this is looking at question 8, which is the tension fabric roof, which is a symmetrical roof which has a mast in the middle or pole and radiating beams or boom elements and tension cables on the edge, which are all fixed to the beams, and it's tied down at the ends of the beams onto foundations. So we're looking at two radii. We're going to look at changing the radius from 15 meters to 7.5. The material is a PTFE, which is covered in the book, so it gives a line load of 7 kilonewtons a meter, which is what we're going to use. It's 6 meters by 6 meters, and we're ignoring the top ring for the design. 2.5 meters are the two split dimensions to the booms, and we're looking at the hints, which we're looking at the chapter 2.7, pages 74 to 75 essentially. Question 8a. And we draw it out, and what we're looking for are the tensions in the cables. And first of all, we have a radius of 15 meters, a line load with PTFE is 7 kilonewtons a meter. So tension in the cable, or edge cables, the same radius. From figure 2.9.20, which is looking at a compression ring, but here we're effectively reversing it if you like. So at PR, where P equals 7 kilonewtons per meter and R equals 15, tension is PR, which is 7 times 15, which is 105 kilonewtons in the cable. Question 8b, and what we're doing here, we're looking at the cable tension. Reference 8a was 105 kilonewtons, that was for a radius of 15 meters. If we apply a safety factor against the braking load, which we find in the tables, which is the minimum braking load, which we find in the website, we multiply 2.5 times the cable load, gives 263 kilonewtons. Now we compare this with the minimum braking load from the chart, and we come up with our cable size, which will match this or meet this of 20 millimeter diameter. The minimum braking load of 380 kilonewtons, which is greater than the 2.263, which is essentially the ultimate load in the cable. Question 8c, and now what we're doing is we're going to draw it out. So if you draw it to scale, and you may need a compass or other means, it looks more comfortable really as 7.5 meters. If you can see, drawing to scale gives a better visual reference point. So again, TC equals PR for the 7.5, which gives you a force in the cable of 52.5, times by the 2.5 factor again, 131 kilonewtons. We compare this with a minimum braking load, we come up with a 12 millimeter McAloy single strand cable, which will actually give you not only more comfortable looking, but neater and smaller fittings because of the loading and the sizes of the end fittings. Question 8d, and we're going to look at this in a little more detail to try to find the boom forces. And if you look at, we're going to work it out for the radius of 15, otherwise known as the set, and we're going to resolve it for the horizontal and vertical forces. If we go back to square one, ignoring the cable force that we found before, and we're going to resolve for the horizontal and the vertical reactions to find from 45-degree resolution the boom forces. So first of all, we find the reactions RH and RV. So we have our cable, we have the loading in it, it's 7 kilonewtons per meter, RH and RV. And the forces diagram, we show the booms there, and we have cables coming in at the booms, so we've got two cables coming in at the boom end, and the span, if you like, for this is L, and the sag or the set is given as H. So we move on to work out from the cable forces the reactions at the end of the boom. So we take, for R15, we can draw out the cable forces and showing the individual cable. For W of 7 kilonewtons a meter, H, which is the sag or the set as the terminology in this type of roof, similar to the rise of an arch. H is 0.3, the span is 6 meters, and for the R15 we're going to calculate what RH and RV is. So we solve for both of these, and we solve it for one cable. So RV is given by, like a simply supported beam, WL over 2, 7 times 6 over 2 is 21 kilonewtons, and RH, which if you look in the main book, Structural Engineering, Art and Approximation, where we solved for a tension cable in a suspension bridge, H is the rise in this case, figure 2.2.7 in the book, WL squared over 8H is RH, so it's 7 times 6 squared over 8 times 0.3, which gives us 105 kilonewtons. So we've now found RH and RV being 21 kilonewtons and RH 105 kilonewtons. Continuing from this, we can resolve for the reactions in the end of the boom, the forces in the boom, if you like, and remembering that we've got two cables coming in at each boom, and the RH for one cable is equivalent to RV for the other, and these are additive, so we've got cables 1 and 2, and the boom is in compression, which is resolved from the cable reactions, and noting that because it's in all internal forces, there's net zero external forces for the system. So finding the boom force is resolving the vector forces, resolved cable reactions from before, from the previous page, we've found, and the boom is at 45 degrees, and we write in those reactions. So the resolved force in the boom, the compression force, is given by the summation of all the reactions, and it's 45 degrees, so it's similar for the RV and RH, it's times cos 45, and we put in the figures, and we have a boom force of 174 kilonewtons, and we just show those forces there, and this is the resolution. As we say, it's 45 degrees in this instance. If it was a different angle, then it would be different resolution for the vertical and the horizontal forces. And finally, we're going to look at, for the radius of 7.5 cable, and not going to show all the calculation, but we know that the vertical reaction, which is similar to a simply supported beam, is exactly the same whether it's R7.5 or R15. We have a rise, which is the set or the sag of 0.63 meters in this case, which we found from geometry, and by calculation again we find that the RV is 21 kilonewtons, and RH is 50 kilonewtons, noting that RH is very similar to the cable force that we found before, and the boom compression comes from the summation of these, cos 45 for 2 cables, and if we work this out we come out with a boom force of 98 kilonewtons, which is approximately half the boom force for the radius of 15.5. So here we are, and the question is, does this make any difference to the resolved to the system? Because it's all internal, there are no external forces on the system, so the overall balance is the same because all the booms will react with each other. It's all in equilibrium. I trust this was clear, and thank you for listening.